Good morning. I will start this video by redoing a problem that I had done before. Part of it was correct, the other part was incorrect. So let me redo the entire problem so I clear up any issues that students may have, any questions you may have. A sample of 36 data values x gives sum of x minus 45 is negative 148, and sum of x minus 45 all squared is 89. Calculate estimates for the mean. Now, they obviously meant the mean of x. Well, what we're going to first start doing is, this is a problem involving what they call coding, where you have a linear relationship between the variable that you're interested in and another variable that you're going to introduce. And I'm going to introduce another variable called y, and y will be x minus 45. What would that mean? That would mean that the first expression, sum of x minus 45 becomes sum of y is equal to minus 148. And the other expression becomes sum of y squared is equal to, sum of y squared is equal to 3089. Okay, so far so good. And now I'm going to find y bar, because y bar is equal to the sum of y divided by n, which in this case is minus 148 divided by n is 36. You have 36 elements there. Now, this is the true value. I don't want to break it down. I'll keep the full value, unless it's a whole number. No, I'll keep the full value. So that's y bar. But I'm not interested in y bar. I'm interested in x bar. And you would remember from when we did probability theory, this expected value, we had a linear relationship, and we found the relationship between the two expected values. Well, expected value is nothing more than mean. So I'm going to use that notation because I know you're familiar with it. If I were to write back the equation y is equal to x minus 45, then the expected value of y is equal to the expected value of x minus 45. The expected value notation or sign distributes over addition and subtraction. So that becomes the expected value of x minus the expected value of 45. Okay, the expected value of y is equal to the expected value of x, and the expected value of a constant is that constant. And therefore, if I make expected value of x the subject, that would be equal to expected value of y plus 45. But expected value is just another terminology for mean. Therefore, the mean of x, expected value of x is the mean of x, which I'll call x bar, is equal to the expected value of y, which is y bar, plus 45. And therefore, x bar, which is what they want, is equal to y bar, which I found earlier, minus 148 over 36, plus 45. When you crank the handle on that, x bar is equal to, the full value is 1472. I worked the numbers out. 1472 divided by 36, which is 40.9 to three significant figures. There, that's x bar. What are you doing? Huh. Okay, I guess I can't do that here. All right, I wouldn't try. All right, so that's X bar. Put a regular border around it. The next part, they're asking for calculate the estimates for the standard deviation of the data. So they want the standard deviation of X. Well, first let's start with the variance of Y. Variance of Y, which I'm going to call SY squared. Remember the regular formula? It's the sum of Y squared upon N minus Y bar, all squared. And I don't have the sum of X squared. I have the sum of Y squared. Sum of Y squared, which is the same as the sum of X minus 45 all squared. So I plug in the numbers. SY squared is equal to 3089 divided by 36, still have 36 data values, minus Y bar all squared. The full value of Y bar was minus 148 over 36. Minus 148 over 36. I think I messed up when I did it the last time. I think I had minus 48 over 36. So that was an error to begin with. All right. When you crank the hand on all of this, you get SY squared, which is the variance of Y. The full value is 22,325, all divided by 324. 324, that's correct. If you wanted the decimal value for that, that would be 68.9. The three significant figures. All right, so that's SY squared. Now, the question is, what's the relationship between the variance of Y and the variance of X? Because at the end of the day, that's what we really need. From the variance of X, we can therefore find the standard deviation for X. So, if Y is X minus 45, as we had before, then var Y, variance of Y, that's another notation you can use for variance, is equal to var of X minus 45. And we know if var distributes over addition and subtraction, var Y becomes var X minus var of a constant. The variance of a constant is 0. We all know that. So so that's what it is. I'll go back to the old notation. SY squared must be equal to var X, which is SX squared. The variance doesn't change if you subtract a fixed value from all of the data values in your data set. So variance of X is also 68.9. And the standard deviation, therefore, let me squeeze it in here before I get to the next section. And therefore, the standard deviation of X, which is SX, is equal to the square root of that variance. And that value ends up being 8.30. Let me double check. Yes, 8.30. So that should have been the true value for the standard deviation of X. Right? Okay. Let's go to the next part. Another data value X equal to 29 is added to the values. Calculate values for the mean and standard deviation of the 37 values this time. All right, so let's start with the mean. And now that we have the mean and the variance for X, right, var Y equal var X, which is the 68.9, or I'll put the full value here, 22325 upon 324, and then the 68.9. we don't have to go back to y anymore to find the mean and the variance for the 37 values of x. Yes, that's where, even though it could be done, it's not necessary to go back to y. So let me summarize what I have. I have x bar, the mean of x, as being 1472 upon 36, which is 40.9. And I have Sx squared is equal to 22325 upon 324, which is 68.9. I'm going to use that information to find the mean and variance for the new values of x. X bar, the new set of values for x, including the 37th value. X bar, we know that that's sigma x upon n. Therefore, x bar I know to be 1472 upon 36, and that must be equal to sigma x upon 36. Which makes sum of x just 1472. So I know sum of x on its own for the 36 values. New sigma x would be equal to the 1472 plus the value, plus the 37th value, which is 29. If I add in, they said it right there, x is 29, the other data value. When I add that in, 1472 plus 29, I can't add. It's 1501. So now that I have the sum of x for the 37 values, I can find the new x bar. New x bar is equal to new sigma x upon n this time, which is 37. So that's 1501 upon 37. New x bar, 1501 upon 37. And the decimal value for that is 40.6. The mean went down a little bit. You added an extra value, but the value is smaller than the original mean. So it makes sense that the mean went down. Should be able to put a box around you though, right? This time I can put a box around you. Yes. So that's the new mean. Notice I keep both the full value and the decimal value to one decimal place. When you're calculating variance, you should always try to use the true value for the mean. All right. Now the old Sx squared, the formula would have been the sum of x squared upon n minus x bar all squared. I know Sx squared. It's right up here somewhere, 22325 upon 324. Sure got that right, 22325 upon 324. And that must be equal to sigma x squared. All this is dealing with the old stuff. Upon 36, and it's 36, minus x bar all squared, the old x bar. The old x bar, the full value was 1472 upon 36. All squared. Like so. Out of all of this, I'm trying to find a value for sigma x squared, the old sigma x squared. So if I transpose, I'll get 22325 upon 324 minus, that should be plus, 1472 upon 36, all squared. And if I divide all of that by 36, that should give me the old sigma x squared. And the value is yes, I did this calculation beforehand and they didn't give it to me. Oh, they did. Sorry. 62,669. Just double check my values. 62,669. That would have been the sum of the sum of the squares of the first 36 values. Now I need a new sigma x squared. I'll double check this value, but I'm pretty sure that one is correct this time because I double checked it before I even started the video. Okay, the new sigma x squared would have to be 62,669 plus, I remember the 37th value is 29, so I have to add the square root of that, 29 squared. When I crank the handle on that, I get 63,510. Yes, double checking, 63,510. So that's the new sigma x squared. And therefore, the new Sx squared would have to be the new sigma x squared upon n minus the new x bar all squared. I hope you understand my notation with this new business. All right, so new Sx squared is equal to the new value for sigma x squared, which we just found to be 63,510. Divided now by 37 minus the new x bar, which is 1501 upon 37, all squared. When we currently handling that, we get 70.75. My calculator refused to give me that as a fraction, so y'all are better using that calculator than I am. So you can figure out if it can give it to you as an improper fraction. I got 70.75, if I can write. And when I found the square root of that, new x bar, new Sx, new standard deviation, that ended up being 8.41. So there. But they want the standard deviation or just the variance? Calculate the value of the mean and see a standard deviation of the 37 values. I think I can pretty much vouch for these numbers, but you know, y'all can double check them and tell me what's what. The concept is totally correct, and I think the numbers are correct as well. So that takes care of that problem. Let's keep moving. I want to start a new, well, this is within the same video, but we're continuing with sampling. I think I had done a video before, not I think, I know I'd done a video before involving populations and, populations and samples. Well, this video is going to deal with random sampling techniques. And let's keep going. These are the sampling techniques in which sampling units are selected with a known probability of selection. So there's going to be a known probability with which each value could be drawn. And we're going to start with the most basic one, which is referred to as simple random sampling. Simple random sampling. Let me neaten this up a little bit. Okay. What is simple random sampling? Each sampling unit has an equal chance of being selected. And the procedure is pretty simple. Assign to each member of the sampling frame. We talked about that before, what the sampling frame is. It's a means of identifying all of the population elements, like a list of some kind. School's register, for example. Assign to each member of the sampling frame a sequential number, and then select the sample using a random number table or a random number generator. That's it. Here's my example to show how that works. Use a random number table to select a sample of 10 people from 100 people using simple random sampling. So what would you do? Assign to each person in the population of 100 people a sequential number from 00 to 99. From 00 to 99, that's 100 numbers. So first person gets 00, second person gets 01, 02, 03, 04, all the way up to 99. So each person has a little paper or something, or at least somehow they know what number is assigned to them in sequence. So you can line them all up and just give them the numbers in sequence. Now, how does this process become random? Select two-digit numbers from a random number table, either going row-wise or column-wise. Well, here's a random number table I have imported into this document. A random number table is exactly what the name suggests. It's a table of random numbers. And whether you select numbers in sequence from the random number table, or you select random numbers at random from the random number table, the numbers that you end up with will still be just as random in either case. There are other scenarios in which you can generate random numbers. It's called a random number generator. I remember when I like to tell this story. I was working at GT&T for a number of years, and the first set of phone cards that came in, I think they had 12-digit pins, and we had a random number generator that would simply generate random numbers to assign to each one of the phone cards. Was it a 12-digit pin? Yes, a 12-digit pin. If you think about it, any 12-digit pin is going to have how many possible phone cards could you have if you're using 12-digit pins? Well, if you can choose from 10 digits, 0 to 9, and there are 12 such, and there are 12 digits, it's 10 to the power 12. That's a whole lot of cards. And we would do them in batches of, I think, like 5 million at a time. 10 to the power 12 is 1 with 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Mercy. 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is, let me see, million, billion, trillion. 1 trillion cards with a 12-digit pin. And I think later on, probably that was after I left, they bumped it up to 16-digit pins. So it's very, very difficult to try to guess pin numbers. We used to be hearing all these fancy stories about how these bright boys at UG were doing some fancy math and figuring out our pin numbers. Yeah, let them go. They can figure out. That never really happened. Those are just rumors. Anyway, let me get off of that story. let's get back to this. So random numbers can be generated from a random number generator, and they don't have to be 2-digit numbers like I have in this table here. They can be 12-digit numbers, 16-digit numbers, any number of digits that you want. Okay, so I'm saying select. I've assigned to these 100 people 2-digit numbers from 00 to 99, and I'm going to select 2-digit numbers from the random number table, either going row wise or column wise. Usually in the exam, they would tell you which row to start at, which column to start at, and if you should go down a column or across a row. Whether you go down a column or across a row, the numbers that you would generate would be just as random. Now, if in the set of numbers that you pick, you see a number that repeats, you simply skip it and go on to the next one. Okay, now, here is how I want you to generate your random numbers from this table. And everybody obviously will end up with the same set of random numbers. If you're going to start at the 6th row, the 3rd column, and we're going to go row-wise. So the 6th row, 1, 2, 3, 4, 5, 6th row, 3rd column. And go row-wise. So that first number is 92. Then 99, then 60, 97, 53, 55, 34, 01, 1, 2, 3, 4, 5, 6, 7, 8, 43, and 40. So whoever had these 2-digit numbers, they will be picked in my sample of 10. There's no reason I couldn't have started at any other row or any other column and gone column-wise, for example. All right, so this is the sample of 10 that I just picked there using simple random sampling. By the way, on your calculator, there's a button that allows you to generate random numbers as well. I'm not 100% sure how to do it. Let me see if I can random 0.014, 0.432, 0.016. Yes, invoke the random number generator. It gives me, in this case, I'm getting three-digit random numbers. It's giving me as decimals, but no problem. 0.599, 0.732. Try it out on your calculator and see what happens. You can generate 3-digit random numbers from that. And by the way, suppose I had needed 3-digit random numbers from this table, or 4-digit random numbers from this table. What would you do? Well, for 4-digit random numbers, you simply squeeze two 2-digit random numbers together. So, for example, if I had started same row, same column that I had started at, then the first 4-digit number would be 9299. It probably would be more favorable if you were doing 3-digit numbers to go column-wise, where you strip off the first digit from the number that's parallel to it and you go down a column. So my first 3-digit number there, if I started at the same row and same column, would have been 929 and then 492 and then 113 if I'm going down the column there, like so. So it's not difficult to take a 2-digit random number table and generate random numbers that are larger. No big deal there. Okay. Enough about simple random sampling. Let's talk about stratified random sampling. Procedure is as follows. Let me tidy up a little bit. Yeah, stratified random sampling, the procedure. Split the population into subgroups or strata, where the subgroups are as different from each other as possible. That's the first part of the procedure. Select a random sample, usually simple random sampling, usually a simple random sample, from each stratum in proportion to the number of items in that group. And step 3, combine the samples to form an overall sample. So let's see. I took this example from the text. I thought it was a pretty good example. Very simple and to the point. Makes the point very well. So here it is. A company employs 320 drivers, 80 office workers, and 40 mechanics. Use an appropriate sampling technique to select a committee of 11 to represent all office workers. Let's think about it for a second. The subgroups that I may want to break this up into are clearly defined right there as they are. The group of drivers, the group of office workers, the group of mechanics. So that when I pick a simple random sample from each of those subgroups, I'm pretty sure that each one of the groups will be represented in my sample of 11. That makes sense? So stratified random sampling seems perfect for this because the strata are effectively already defined. The group of drivers, the group of office workers, and the group of mechanics. Now, according to the procedure, I'm supposed to select from them in proportion to the number in that group. So, what's the total number of people that work at for this company? 320 plus 80, that's 440? Yes, 440. So there are 440 people that work for this company. Okay, so I need a committee of 11. So for the drivers, or from the drivers, I'll choose the ratio 320. There are 320 drivers out of the total times 11. I'll choose 8 drivers. From the office workers, I'll choose 80 out of 440 times 11. That will be 2 office workers. So I already have 10 people here. And let me just verify by the same calculation, even though I know I'll just be choosing one from the mechanics. But I'll go for mechanics. 40 over 440 times 11, and that should give me 1. So that's how I'm going to choose my sample of 11. Sample of 11, 8 drivers, 2 office workers, and 1 mechanic. Everybody will be represented in this sample. Okay. And as an advantage, every subgroup within the population is represented. I have it right there. Good. So the mechanics, the drivers can speak up for whatever problems the drivers are having and so on and so forth. Same for the mechanics and the office workers. The next type of sampling technique I want to look at. Oh, and by the way, the 8 drivers will be chosen using simple random sampling, right? The sampling technique I discussed above. Same for the office workers and same for the mechanics. Let's go to the next sampling technique, which is systematic random sampling. Okay. Procedures as follows. List the population in some order, alphabetical order, order of ranking, or order of completion, and maybe a conveyor belt. Whatever order that you choose. Order of ranking, by the way, ranking, you know what ranking is, right? I don't know if they still do it. At the end of every term, I remember on your report card, they put what place you got in class. I remember, let me see, I remember all my first and second form ranks. I got 11th, 20th, and then 30th, 11th, 16th, and 20th. And by the time my ranking went to 30th, my father said, okay, it's over for you now. And he turned the screws, and things got better after that. Moving right along. So that's ranking. Order of completion on a conveyor belt. Typical example I know of that would be like you go to the airport and you're picking up your bags, and you see them coming around in this circular belt, and as your bag passes, you pick it up. Yeah. Well, immigration might use. I'm assuming. I think they do some kind of random technique where they identify a couple of people whose luggage they want to check, and they may very well use some random sampling technique. Okay, what's the advantage of using systematic random sampling? I haven't even finished the procedure. Let me go again. List the population in some order. Example, alphabetical order, order of ranking. I discussed a little bit about that. Order of completion on a conveyor belt, etc. And then you choose the starting point randomly. So I might choose the 5th bag that comes around on that conveyor belt, or the 7th bag that comes around, or something of that nature. And then you choose the other sampling elements at a fixed periodic interval, every kth element after the fixed starting point. I'll explain that a little bit more as we go along. The advantages, it's quick and easy, or quick and cheap. Quick and easy to check for errors. Disadvantages, it is possible for any periodic or cyclic process to introduce bias. I think we discussed bias in the previous video. Example, if the 8th item is faulty and you choose your period to be 8, then it's possible you have problems. So here is my first example. Choose a systematic random sample of 25 items from a group of 100 items. So what I'm going to do, I'm going to organize the list from 1 to 100. The same idea. Similar idea. I'm going from 1 to 100. And then what's my kth item? Well, if I'm choosing 25 things out of 100, then I want to choose every 4th one, right? 100 over 25. Choose every 4th item from this, and I am choosing a random starting point. I have just chosen 5 for my random starting point. You could have chosen some other point, 17 or some number like that. So I've chosen 5, the 5th item, as my random starting point, and then every 4th one that comes along after that. So the 5th, the 9th, 13th, 17th. Let me do at least 2 more. I hope I'm counting right. 17 and 4. 21st, 25th, 25th, and so on until I get all 25 of my items. By the way, what happens if you get to the end of the list and you still have others to choose from? Then you wrap around and you come back to the beginning of the list. So let's say the 24th item, let's say whatever random starting point you had chosen, the 24th item was 99. Then 4 from that will be 100, 1, 2, 3. Right? You could wrap around back to the 3rd item on the ordered list. That's pretty straightforward. Now, what happens if you choose a systematic random sample of 30 items from the group of 100? Well, you kind of do the same thing. You organize the list from 1 to 100. Now, your interval will be, instead of 100 over 25, when you were choosing 25, it's now 100 over 30. So you choose every 3.3 or 3.3 item from the ordered list from a starting point of, and I'm going to choose 7 as my random starting point. Okay. So let's see how that goes. If I choose 7 as my first one, so the first choice is 7, the 7th item. Then I have to add 3.3 to that. So 10 plus 3.3 gives me 10.3. So I round down and I choose the 10th. Then the next one is 10.3 plus 3.3, which is 13.6. So I round up and I choose the 14th. I'll do 2 more. Next one is 13.6 plus 3.3. 13 and 3, 16.9. So choose the 17th item. And one more. 16.9 plus 3.3. 19, 20.2 it looks like. So I choose the 20th. What's wrong with this pen sometimes? Choose the 20th. And so on and so forth. You can do a couple more just to make sure you get the idea. So my list would be the 7th item, the 10th, the 14th, the 17th, the 20th, and so on. All right, notice the gap sometimes is 3, sometimes the gap is 4. And that's because you either have to round up or round down. In this case, it's not a nice interval of exactly a whole number. All right. That's all I want to say about systematic random sampling. And that's the end of the random sampling techniques that we're responsible for. The non-random sampling techniques, I can show you here. This is going to come in the next video. Deals with cluster sampling, quota sampling, purposive sampling, snowball sampling. And we're going to run, those are more theoretical, a lot of explanation. So I want to do a totally different video for that and give examples. And I'm going to stop this video right here. Okay, I'm out.